Hello everyone, um, welcome to my YouTube channel, Chemical Engineering by Atkins. So today I'm going to be taking you through the use of ASPEN HYSYS, which is a simulation model to simulate a fire heater. So we have four main objectives for this video. So one, we're going to determine the fire heater duty, and two, determine the amount of fuel needed, three, determine the amount of air needed, and then finally to determine the composition and the amount of flue gas that is produced from the combustion process. Okay, so let me get into ASPEN HYSYS. I'm sure most of you are familiar with the simulation tool. Okay, so the main purpose for this simulation is to give an indication in industry, because we would want a situation where you running your processes at the least possible use of utilities. So mainly in a fire heater you use fuel and air to handle the combustion process. So in this case we're going to make use of fuel, which is mainly composed of methane, natural gas with 100% methane, and the air is going to be composed of 79% nitrogen and 21% oxygen. Okay, so we're gonna start right now by adding the components of our feed. So our feed is basically gonna be containing natural gas, which is normally a combination of methane, water, carbon dioxide, carbon monoxide, nitrogen, hydrogen, and all other higher hydrocarbons, depending on where the natural gas is sourced from. So okay, we're gonna start by just adding a general natural gas composition by adding methane, okay, water, nitrogen, oxygen, carbon monoxide, ethane, propane, okay, the other higher hydrocarbons, iButane, N-butane, pentane, hexane, heptane, octane, hydrogen sulfide. So most natural gas most natural gas that is sourced from its surface contains a lot of hydrogen sulfide, isn't it? It's considered an impurity as well. So hydrogen sulfide, and hydrogen. So the next thing to do is to specify the fluid package, and considering that there is a lot of hydrocarbons in our feed, the Peng-Robinson model is used because it's one that is compatible to handle hydrocarbons. Peng-Robinson, okay, there's it. Okay, so the next step will be to move on to the simulation stage. Okay, then you see there on your left hand side there's the model palette, and then looking straight for fire data. Now there's it, fire data. Okay, so you can immediately identify your fire data by labeling it whatever you want. Maybe I'm gonna label it fire data. Okay, so the feed stream, I'm gonna label it feed. In the outlet stream, I'm just gonna label it outlet. And then, as you are aware, you may be aware, for fire data you need to have a fuel and air for the combustion reaction. So I'm gonna label the fuel stream as natural gas. Let me say fuel natural gas, and then the air stream, I'll just label it air. And then you know that from the combustion reaction there's a flue gas that is associated with combustion reaction. So yeah, okay, let's position our stuff. Okay, so now it's time to specify the streams. So the main objective in this presentation is to determine the amount of fuel natural gas needed, the amount of air needed, and the amount of flue gas that is produced. In order to elevate the temperature of the feed stream to a specific temperature in the outlet stream. Okay, so let's specify the feed stream, because in this situation the fire data is just acting as a heat exchanger to elevate the temperatures of a feed stream to an extremely high temperatures. Like in this case, we're gonna be moving from 480 degrees Celsius in the feed to want to get to a temperature of around 1000 degrees Celsius in the outlet stream. So let's specify the feed. Okay, so the feed is entirely a gaseous stream, so the vapor fraction is 1. And then the temperature is coming in at, let's say, 480 degrees Celsius, and the pressure maybe at 20 bar. That's about 2000 kilopascals. And then the molar flow rate, maybe let's say 261 kilomoles per hour. Right, and then after that we then move on to specify the composition of the feed. So our feed is going to be having 86% 86% methane, and then 5% water, 2% carbon dioxide, 2% nitrogen, and 5% hydrogen. There you have it. You see there it indicates with a green color, so our feed stream is okay. So we immediately go on to specify the outlet stream. Vapor fraction is T1, gaseous stream, and then we want the temperature to be 1000 degrees Celsius, and then the pressure, we assume a slight pressure drop, because really we can't have no pressure drop in exiting the fire data. So we'll say maybe there will be a pressure drop from 2000 kilopascals to maybe say 1948 kilopascals. The molar flow rate does not change. Mass balance. And then okay, now we move on to specify the composition. The composition does not change as well, because all we are doing is elevating the temperature of the stream. Okay, 5% water, 2% nitrogen, 5% hydrogen, and 2% carbon dioxide. Okay. As you can see, the green color showing that the stream is now fine. Okay, now we move on to specify the conditions of the fuel. Still vapor fraction is 1, gaseous form, and the temperature comes in at around 25 degrees Celsius, room temperature, and then at a pressure of around 1 bar, which is 100 kilopascals. And then we want to find out what flow rate that's gonna be, and then we assume that our natural gas, the fuel natural gas, is 100% methane. Okay, you see the flow rate is missing, so there's no green color on that tab, because it's one of our objectives to find out how much natural gas will be needed to elevate the temperature of the feed stream at 480 degrees Celsius to 1000 degrees Celsius. So similarly, we work on our air stream, and then of course the vapor fraction is 1, temperature normal room temperature, and then 1 bar as well, and then the composition of air is having it as 0.79 nitrogen and 21% oxygen. So on the natural gas product, on the flue gas product stream, we don't specify anything, because that is one of our other objective. We need to see the composition of the flue gas and the flow rate of the flue gas as well. So let me just relabel this one flu, guys. Okay, let me close this model palette. Yeah, so the next step would be to make sure that you um, make adjustments to make sure that ASPEN HYSYS knows that you want to model a fire data. So you do this by changing the fire data from